abilities for Lagrangians that obey our general rules. And now we are into our first few exercises in imposing a symmetry, which, as I said, can only reduce the number of terms or of independent terms. And I mentioned in the table in the last minute that discrete symmetries lead to selection rules, that continuous global symmetries lead to conservation laws, and that local symmetries lead to interactions mediated by spin-1 force carriers. So now we will see three examples: a discrete symmetry, a global continuous symmetry, and a local continuous symmetry. And in C, this will demonstrate each of these three consequences and perhaps a little more. This was not erased. So originally, when I started preparing these lectures, I thought I will cover a smaller number of topics, make a shorter program, which was an idea. However, what I decided is that in any case, I'll prepare slides for everything. I'll get wherever I get. And then those of you who are interested can look for the further lectures that you did not hear. So that's why the full table is here. So abelian symmetries, we'll start with global symmetries, discrete, continuous, the concept of charge, first part, second part will come here, product group, accidental symmetries, and fermion masses, and then to the heavier topic of local symmetries. So first of all, global versus local, I mentioned it already. With global symmetry, the symmetry transformations are independent of where in space-time they occur. They are the same everywhere and every time. In local symmetry, the symmetry transformation depend on the space-time coordinate. We'll see exactly what it means and what are the consequences. So let us start with the simplest, I think, of all symmetries, abelian Z2. So we take the simplest model, a single real scalar field, and we saw already the most general Lagrangian for this kinetic term, mass square term, and trilinear and quartic interaction terms. We saw that. And now we say we impose a Z2 symmetry under which phi is odd. So under this symmetry, phi goes to minus phi. Let me make a statement which, I don't know, perhaps it's trivial, but for me it took some time to understand. If you impose a symmetry and all of your fields are singlets, they do not transform under this symmetry. Let's say you impose a Z2 symmetry and all your fields are even under this symmetry, namely they go to themselves, then it's like not imposing a symmetry. It has no meaning, okay? It has no consequence. Some of the fields have to transform non-trivially under the symmetry that you impose in order that it will have consequences, okay? So, I don't know, it's meaningless to say that our universe has, I don't know, a huge symmetry, I don't know, the standard model group times SU5 plus SO10, if all the fields in the nature do not transform under these additional symmetries beyond the standard model, okay? So, just making this side remark. So, phi goes to minus phi. It tells us that odd powers of phi are forbidden because they will go to minus themselves. They are not invariant under the symmetry. And even powers of phi are allowed because they go to themselves. And so, of these terms, this one is forbidden, the trilinear term. And this is what we get. So it's an example that with a symmetry, the number of terms is usually smaller. What are the consequences of this? There is, we can call it phi parity, the number of phi particles related to this, to the power minus 1 to the power of n. And between the initial state of any process and the final state of that process, phi parity is conserved. So, in other words, if you started with an odd number of phi particles, you will end up with an odd number of phi particles. If you started with an even number of phi particles, you will end with an even number. So the number of particles can change only by an even number. So here we see, for example, this lambda to the fourth term. So you can have two such phi particles going into 2, 1 going into 3, 3 going into 1. Every time it changes by an even number. So that's a selection rule, that it can change the number of particles in a process, can change only by an even number. It's not a conserved charge, it's a selection rule. So that's the simplest model and the simplest example of imposing a symmetry. A little bit richer in phenomenology is a global continuous symmetry. So let's start with SO2. SO2 is the rotation in a two-dimensional plane. Now this is an internal symmetry. What it rotates are fields. These are not space-time coordinates. So we can say that we have two real fields, call them phi r or phi I, or, as we'll soon do, combine them into a single complex field, and that will allow us to define charge and to see charge conservation. So the most general renormalizable Lagrangian with two real fields, that I call them phi r and phi I, because later I want to put them as real and imaginary part of the same field. There are, in the canonical normalization, all the diagonal terms, so that's d mu phi r, d mu phi r, and d mu phi I, d mu phi I, and each with a coefficient of half. Okay? In general, we could start with, let's say, even d mu phi r, d mu phi I, but then I would change it to a basis where this is diagonal and have the same coefficient to all of them. All the quadratic terms, so phi r, phi r, phi r, phi I, etc. All the possible trilinear combinations, all the possible quartic. So a lot of terms. I don't know even, certainly not at 3 p.m. to count them. Okay, it's not after lunch, but many, many terms here. But now I impose a symmetry. And the symmetry, SO2, requires that the Lagrangian is invariant under a rotation in this field space. So I operate with this matrix, which is thus the rotation matrix in 2 dimensions, cosine theta, sinus theta, minus theta, cosine theta. So under the transformation of phi r and phi I to this matrix times phi r, phi I want the Lagrangian to be invariant. That reduces the number of allowed terms very significantly. I still have the two kinetic terms, but now instead of 3 or 4 quadratic, I have really only one independent, phi r plus phi I. And all the trilinear terms are forbidden. They will not appear here. And of all these combinations, there is really just one independent coupling. You can see this quadratic term as phi r plus phi I squared. So that's it, just 2 independent parameters instead, I don't know, probably order 10 or 15 independent without this symmetry. So the symmetry, again, is very effective in both forbidding terms and relating terms to each other. So that's the SO2 symmetry, and that's what we call internal symmetry. It acts on the fields, not on space-time coordinates. And now we'll do the same exercise in a different language. So instead of SO2, we will do U1, and it exactly will be the same. So instead of 2 real fields, we combine them into a single complex scalar field phi, just as we did, here. Okay, this is what we now do. So there is a single complex scalar field, and we impose a symmetry which is just a phase transformation of phi. So phi is multiplied by e to the I theta, a phase. Theta is real here, times phi. Phi dagger, the Hermitian conjugate of the operator phi, comes then with an opposite phase. Transforms e to the minus I theta phi dagger. And now I require that under this transformation, I write the most general Lagrangian that is allowed, and that's it, kinetic term. So when we write a complex field, the canonical normalization is with a factor of 1. If you now write this phi as phi r, as 1 over square root of 2 phi r plus I phi I, then you'll get exactly these kinetic terms with a factor of half. Okay, a result of the 1 over square root of 2 here. So just remember that for complex fields, scalar fields, the canonical normalization is y. For real fields, it's half, and it's because of this reason. And mass square term and a single quartic term. If you write phi as phi r plus phi I, you'll get exactly what we got here. So this SO2 for two real scalar fields, or the U1 for a single complex field, are the same, just a different language. And the language of U1 is much simpler to see and to write. So we will always use this U1 transformation for abelian symmetries of interest to us. So SO2 was a rotation in the real plane of two fields. U1 is a phase rotation of a field. Okay, that's a phase rotation. So one thing to remember, there is no way with an internal symmetry to forbid these terms. In particular, there is no way with an internal symmetry to forbid the m squared term. This is different, later we'll see, than the case of fermions, where with a symmetry you can forbid masses. So massless fermions can be understood on the basis of imposing a symmetry. Massless scalars is more complicated. You cannot get them by imposing a symmetry. There is, however, something called Goldstone boson that allows to understand massless scalars, but it's not yet at this stage of imposing a symmetry. And one more thing, whether here we impose e to the I theta phi, or e to the 2I theta phi, or e to the million theta phi, it's exactly will give the same results. So there is, it seems, a freedom. We can do any e to the I q theta phi, where q is a finite number, and it have the same consequences so far. And we can choose q equals 1, which is what we did in the previous example. This will not necessarily be the case when we have more than one field transforming under this U1 symmetry. So the terminology that we use is that we impose a U1 symmetry and assign the phi field into the Q equal 1 representation of that U1. At the moment, it's almost meaningless, this statement. Once we have more than one field, it becomes meaningful. So here we come to the concept of charge within this formulation. And you know the concept of charge from electromagnetism, right? You know electromagnetic charge. And actually, it has two meanings, or two aspects of significance. One is that it sets the strength of the interactions of fermion with the photon. The larger the charge, the stronger the interaction, right? It's E, the coupling constant of electromagnetism, times the charge. Okay? Neutral particle does not interact with it all. It has Q equals 0. And charge 2 acts with coupling constant that is actually twice as much as Q equals 1. So that's one thing, the strength of the interaction. And the second is that it is a conserved quantity. From imposing a global symmetry, we get so far actually only the second aspect. And this is related to the Netter's theorem that I mentioned before. Charge conservation is related to global continuous symmetry. Namely, if we want to embed or encode the conservation of charge in our Lagrangian, then we discover that it has this symmetry. Or if we impose the symmetry, we find that there is a conserved charge. It works in both directions. It's not so complicated, now that Netter told us, not so complicated to prove, but I will just show an example to say why it is. So let's take a theory or model with two complex scalar fields, phi1 and phi2, and assign each of them with a real number qi. And I impose a symmetry. Phi1 goes into the I q1 theta phi1, and phi2 into e to the I q2 theta phi2. So I impose a u1, and I assign each of the two fields with a different representation if you want, or as we'll see in a minute, a different charge. So in a minute we'll see that q1 and q2 are the charges of this field under the u1. So, and the charge of the Hermitian conjugate of the field is minus the charge of the field itself. So phi1 carries charge minus q1, and phi2 carries charge minus q2. And we can always set one of them arbitrarily to what we want, including to 1, as I did originally. However, the ratio between them, q2 over q1, has physical significance, and we cannot change it by hand. We are not allowed to change it by hand. And so we cannot do it for both. This ratio has physical meaning. So the charge qi for each of the field, if you impose u1, that's the beginning of model building, imposing a symmetry. The next step is to tell how the scalar and fermion fields transform under this symmetry. And so assigning the charge qi is this second stage. It's telling us how the field transforms under the u1 symmetry. So, concrete example. I assign q1 equals 1, q2 equals 3. Kinetic terms are always allowed. These mass terms are always allowed. If they carried an equal charge, there would be also phi1 dagger phi2. So the fact that they carry different charges forbids such a term. That's for later use. And now we have these three quartic terms, which will always be there, no matter which charges I assign to the fields. And there is this one term which is actually special for the choice of 1 and 3. So phi1 cubed, phi2 dagger, 1 plus 1 plus 1 minus 3. And the Hermitian conjugate, phi1 dagger cubed, phi2, which is minus 1, minus 1, minus 1, plus 3. That's allowed. And you can, I hope, intuitively see, but also see in your eyes, that every term here, the sum of charges of all the fields that appear in the term is 0. That's actually what I did here, but of course minus 1 plus 1, minus 3 plus 3, etc. Because that is what guaranteed that the product of these fields transforms to itself without a phase when I transform all the fields. That's why it's allowed. But to be allowed, you need that the sum of charges in this term is 0. That's where charge conservation comes in. If the sum of charges of all the fields in a term is 0, it means that the charge of the incoming particles equal the charge of the outgoing particles. No matter if it's 2 going to 2 particles, 1 to 3, 3 to 1, it will always keep this, that the sum of charges incoming and the sum of charges outgoing are equal. That's charge conservation. Okay, so imposing a global symmetry tells us that there is charge conservation. Also, another thing which is almost trivial, if a field carries a charge, it must be complex, because we transform it by phase. Okay, you cannot, so do it to a real field. And real fields can have Q equals 0. Okay, so that's just the 4 types of quartic terms. And you can see that in the various combinations that are possible, incoming and outgoing charges are the same, or the sum of charges of all the fields involved is 0. Okay, so that's U1, the simplest continuous global symmetry. Let's remain with abelian symmetries. We later see what non-abelian symmetries are. And the next thing is to have several factors of U1. So U1 to the n, I impose more than one U1. So let's see an example. Example is imposing U1 times U1. So I take again 2 scalar fields. I impose a symmetry, U1 times U1. I give them names. Yes?
In addition to conservation charge, do we have a quantization of charge?
Not at this stage, no. No, no. You need non-abelian one, then an abelian subgroup of the non-abelian will have quantization. But here, no. So, now, this is under these 2 U1s, so I assign each of them with charge Q1A and Q1B, Q2A and Q2B, the charge under each of the U1 factors. And then the transformation law under this U1 times U1 would be exponential of I. Q1A theta A, Q1B theta B, times phi 1 and phi 2, exponential of I, Q2A theta A, Q2B theta B. B is a name, okay, that I give to distinguish the fact that I have 2 U1s, okay, so it will be clear which is which. I could call them any name I wanted, okay, X and U1 X, U1 Y, U1 electromagnetism, U1 muon number, as we'll see later, whatever. And now we set an example of these charges. So I set the charge of phi 1 to 1, 0, so it transforms only under U1A transformation and remains itself under the U1B transformation. And for phi 2, I do the opposite, 0, 1, which means that it transforms only under this theta B that appears here, and not under the theta A transformation, because here it has charge 0. And then the most general Lagrangian, again, here it's still diagonal and universal, okay? I use universal for the case that for all fields, the coefficient here is the same. So if you do a U1 transformation for fields that are transformed, that are in the canonical normalization, the transform field will also be in a canonical normalization. They will also be diagonal and universal. All diagonal, 1, 1, 2, 2, and the normalization is 1. I have a mass square term for each of them separately. Phi 1 dagger, phi 2 violates the symmetry. The 2 symmetries actually, both U1A and U1B. Carries charge 1 under each of them. And here I have 3 types of terms. Phi 1 dagger, phi 1, phi 1 dagger, phi 1, phi 2 dagger, phi 2, phi 2 dagger, phi 2, and phi 1 dagger, phi 1, phi 2 dagger, phi 2. These are the 3 allowed terms. And, okay. I skip this, because we are coming into technicalities, and go into accidental symmetries. So I consider a model with the 2 complex fields, scalar fields, phi 1 and phi 2. I impose a U1 symmetry. Yeah, that's the model building, and I have to set the charges of the fields that I included. So I give one of them charge 1 and the other charge 4. And now we'll understand why I made this. Soon you'll understand why I gave the example of U1 times U1. So perhaps it was not clear why I do this complication, and soon it will become clear. So it allows the kinetic term for each of them, mass square term for each of them separately, and these three quartic terms, 1, 1, 1, 1, 2, 2, 2, 2, 1, 1, 2, 2. And this is exactly the same thing that I got here. It's exactly the same thing. Here I imposed U1 cross U1. Here I imposed just a U1. So I imposed the U1 with a specific set of charges, and I got a larger symmetry in my Lagrangian. I imposed the U1, and I got two U1s. So that's an accidental symmetry. I got an extra symmetry. I did not impose two U1s, I imposed one, and I got U1 times U1. So an extra U1 is accidental. It would be broken if I would have allowed non-normalizable terms. So the accidental symmetry is a result of the imposed U1, the specific charges that I gave to these two fields, and the fact that the Lagrangian is renormalizable that I considered. If I would have allowed non-normalizable terms, I could have a term phi1 to the fourth, phi2 dagger. This is a dimension 5 term. It has 5 scalar fields, a product of 5, so it's non-renormalizable. And it would have broken the extra U1. Okay, so that's the typical thing with accidental symmetry. They are a result of three things: the imposed symmetry, the set of charges or representations, as we call them later, when we include non-abelian symmetry, and the fact that we do not include non-renormalizable terms. And then we get accidental symmetries, and in general, non-renormalizable terms will break them, but we do not include them. What it means, by the way, in the phenomenology of effective field theory is that the effect of this is suppressed, typically in a process by E over lambda, where 1 over lambda is roughly the scale of the coupling of this term, because it has to have mass dimension -1, 1 over a scale. E is the energy of the process, so it will be a small effect. Many times, if the scale lambda is very high, negligible, and we can forget about it, sometimes we can see if we make a precise enough measurement, and we can see this small effect of the normalizable terms. So this is just the general thing. If you have a U1, two fields, Q1 and Q2, the sum of charges, let's say that they are positive integers, they do not divide. None of them is you cannot factorize the other into the other one, so it's not 6 and 3 or 6. And so they are co-prime, it's called. In this case, you will always have a U1 cross U1 symmetry in the renormalizable terms, and a term, non-renormalizable one of this type will break the symmetry. One more concept. I'm sorry, many new terms, a lot of new language. As I said, you'll have to look back into it. This is important for fermion masses, so that's why this concept is introduced. So a chiral symmetry or vectorial symmetry refers to the fermions, if you have fermions in the theory. Otherwise, there is no chiral and vector. So we said that we have left-handed fields and right-handed fields. 1 minus gamma 5 times psi and 1 plus gamma 5. And these are independent fields. You can assign them independent charges. So there is no a priori, no relation between the transformation law that you decide for psi right and the one that you decide for psi left under U1 or any other symmetry. The bars, I remember psi bar is psi dagger times gamma 0, where gamma 0 is a Dirac matrix. So the bars carry the opposite charges. And I mentioned before that there is psi left C bar, which transforms exactly like psi left, and psi right C bar, which transforms exactly like psi right, so they carry the same charge. So if you have, say, a single psi left and a single psi right, you call the symmetry chiral if Q left does not equal Q right. That's the name. And you call the symmetry vectorial if Q left equals Q right. That's if you have 1 and 1. If you have several of them, it's a little bit more complicated. Vectorial symmetry is you must have an equal number of left-handed, left chirality and right chirality, 3 and 3, 1 and 1, 10 and 10. And you can match them into pairs where each, say, of the left-handed fields has a pair right-handed field with the same charge. Only if you can do it to all, then the symmetry is vectorial. If you cannot do it, the simplest thing is that there is a different number of left-handed and right-handed fields, and we'll see that actually for neutrinos, for example, when we come to it. Then already it's chiral, or if they are equal number, but you cannot match all of them into pairs, there is even just one pair that cannot be matched, a single left-handed with charge 10 and a single right-handed with charge 3, then the theory is chiral. In any chiral theory, parity and charge conjugation are guaranteed to be violated already by the charge assignment. Okay? There is no parity and there is no charge conjugation in a theory where you cannot match all of them into pairs of equal charges. In a vectorial theory, it depends on the theory. It's not the opposite situation. It's not that in a vectorial theory P and C are conserved. It depends on the details of the theory. They may be conserved or they may be violated. Okay. We saw that for fermions, there are 3 types. If you have psi left and psi right, there is a Majorana-Mess theorem for psi right. And I remind you that as far as transformation properties are concerned, you can read this as psi right, psi right. Okay, this is exactly the same transformation as psi right. A Majorana-Mess theorem for the left-handed chirality. Again, you can read this as psi left, psi left. And a Dirac-Mess theorem, psi left bar, psi right. And let's impose a U1 symmetry with one left-handed and one right-handed, and give them charges Q left and Q right. So you can see that a Dirac-Mess theorem would be allowed only if Q left equals Q right. Right? It's this term, psi left bar carries charge minus Q left, psi right charge plus Q right, and so this term carries charge Q right minus Q left. Its Hermitian conjugate, the opposite. It would be psi right bar psi left, so it will have psi Q left minus Q right. If Q left and Q right are equal, it carries charge 0, and then it is allowed. If they are not, this term is not allowed. So you can, if you want, to forbid Dirac-Mess term if Q left and Q right are not equal. In a chiral theory, some of the fermion fields will be massless or will have no Dirac masses. It's even simpler to forbid Majorana-Mess terms, because if this is psi right times psi right, if psi right carries a charge different from 0, this term is not allowed, because the term carries twice the charge of psi right. If psi left carries a charge, then this term is not allowed, because it carries twice the charge of psi left. So, if I have fermions that are charged, and they are chiral, Q left does not equal Q right, the theory predicts that they are massless. Another way to say it, if there is an empirical fact of massless fermions, then very likely they are charged under the symmetry and they are chiral under the symmetry. Otherwise, some of the mass terms would be allowed. All allowed terms should be included, and we have no way to understand, if there is not the case that they are chiral and charged, to understand why they are massless. Again, this is technical, so I'll skip this. Okay, so what we've seen so far, imposing the example of Z2 symmetry, we got here a selection rule. With a continuous symmetry, we saw the first aspect. We got, first of all, the concept of charge. It has to do with the transformation law under AU1. And second, we saw why charge as a conserved quantity arises when imposing a U1 or any number of U1 symmetries. We saw accidental symmetries. You impose a U1 in our example, and you get U1 times U1 in some cases. We saw both the general conditions for that and an explicit example. And we saw that Dirac masses are forbidden with a chiral charges, Q left different from Q right, and Majorana mass terms for any charged fermion under a symmetry. If you have U1, let's say, cubed, it's enough that the field transform under one of the U1s, a fermion field, in order that it cannot have a Majorana mass, okay? It doesn't have to have charge under all three. Any symmetry under which it transforms, or abelian symmetry, transforms non-trivially, has a charge, then Majorana mass would be forbidden. So that's consequences of imposing a global symmetry. And now we go to the more interesting case of a local symmetry, as we will soon, I think at the end of this, I will tell you that we impose, the standard model has, the only imposed symmetries are local symmetries, and it has much more far-reaching or dramatic consequences than the global symmetries. Not that having charge conservation is a little thing, that's a global symmetry, but local symmetries is really, for me, amazing what it tells us.
Sir, can you just revert back to the previous slide? I had a question. Yeah, so in this Lagrangian, we have terms like psi L bar conjugate and psi L, right? And also the Dirac mass terms. So can we have a term like of the form psi L bar conjugate psi R? That kind of term?
You mean psi right bar, psi right, without the C here?
So left and right.
No, psi right bar transforms like a left-handed field, and therefore that violates the Lorentz group.
Okay. That doesn't
psi left C bar transforms like a left-handed field. Okay, these two things, the C and the bar, makes it transform like a left-handed field, and from psi left, you can, okay, if you know this SU2 cross SU2 way of presenting, psi left is half zero, psi right is 0 half, so you need either two left-handed or two right-handed things in order to be able to make a singlet. If you have left times right, you get half-half. So that's not what you want. So psi left bar transform like psi right, so you can do it. Psi left C bar transform like psi left, you can do it. Psi right C bar, if you want, transform like psi right, and you cannot combine it with psi left.
It's related to the transformation of the fields. It's related to the transformation of the fields themselves.
So?
Yeah, so that's what I'm saying.
Okay. The Lorentz transformation of the fields forbids that. Okay, so local symmetry. We already said that the symmetry transformations depend on space-time coordinates. So here it is how it goes. Again, with the simplest example of a U1. I have to say I will skip here detailed proofs, because detailed proofs would take time and are difficult to follow in such a lecture, so you can reproduce the proofs on your own at home. Consider a complex scalar field, phi. Impose a local symmetry. So theta of this transformation is now theta of x. Okay, could be pi here and I don't know 3/2 pi's there, and it changes continuously between these values. And again, phi dagger goes with minus IQ theta of x phi dagger. So first, if a term in the Lagrangian does not involve a derivative, and it's invariant under the global U1, under the same thing where theta is a constant of x mu, then it would also be invariant under the local symmetry. Okay? Phi dagger phi, the quadratic term, for example, whether theta is x dependent or not, you can see that phi dagger phi, this minus IQ theta of x and plus IQ theta of x would cancel in the exponent, and the term will be invariant. Same for the quartic term. You cannot write a trilinear term with such a transformation anyway, so the quadratic and the quartic terms, if they are invariant under the global symmetry, then they are also invariant under the local symmetry. It requires only that the sum of charges in the term is zero, in terms without a derivative. This is not the case for the derivative terms. So the derivative terms is d mu phi dagger, d mu phi, in this case. So let's see what happens here. So d mu phi dagger is d mu after the transformation, d mu acting on e to the I q theta x times phi of x, the transformed field under the symmetry transformation. Part of it is e to the I q theta d mu phi, as it was before for the global, but now this d mu acts also on theta, which is x dependent. Before it was constant, so the derivative of that was zero if you want, but now it's no longer zero, so we have here e to the I q d mu of theta and e to the I q theta phi. So there is this additional term, and it doesn't cancel when you consider the product in the kinetic term, how the d mu phi dagger, d mu phi transform. There are additional terms, both d mu phi times this d mu theta. It doesn't cancel against d mu phi dagger, d mu theta, and the product of these d mu theta. So 3 new terms that were not there originally. So the kinetic term is not invariant under a local symmetry. So if we didn't have a way to fix it, or naively we would think that if kinetic term violate a local symmetry, and we want to describe particles that propagate in space-time, and we must include kinetic terms in order to be able to describe that we cannot impose local symmetries, right? So, however, turns out that there is a way, and there is a single way to fix it, and that single way seems at first sight contrived, or surprising, or what the hell, what are you doing? Except that it applies in nature. And then, okay, if that's the only way, and if nature seems to do it, nature seems to like local symmetry and to fix this non-invariance by doing something, then, okay, that's what we should do. So, it seems to forbid L-kinetic. We want to keep L-kinetic because we want to be able to describe free propagation. We don't want to give up on it. Can we fix it? Can we have dynamical fields transforming under a local symmetry? And the answer is yes. As I said, we need to keep it. And now we had additional terms, and we want to cancel them against something. Right? The kinetic term is there. These additional terms, when we do the transformation, are there. You want to add something, do something that will cancel against them. If we were able to replace this del mu phi with something, I give it a name, d mu phi, because among other things, this d mu has to include that partial derivative to keep the kinetic terms originally there. But it's d mu plus allow me anything, okay? And we'll see in a minute what's this anything in. If we were able to construct such a creature, d mu phi, that would transform the same way that the kinetic terms transforms under the global symmetries, then we are fine, because if that's the transformation, this is now theta of x, d mu phi dagger, d mu phi would be allowed if we can have this transformation law. Okay. So here is how it goes, okay? So, as I said, you can prove it in more detail. I'll just tell you what's the only way to do it. So you add, you create this creature d mu by doing the following. Del mu plus I G Q A mu. Q is the charge of this field phi. So G is a dimensionless constant. You are allowed to put it there, and if you are allowed, you put it there. Okay, so it fixes for whatever value of G, so it's okay. And A mu is a vector field, a spin 1 field, with the following transformation law. So two things. Why do we add a vector field? Because it has to come together with this del mu. It has to have this index mu in it. Okay, it has each of the four components of d mu, d to dt, d to dx, d to dy, d to dz, by itself already give non-invariance. So each of these has to be compensated for, and that can only be done by still keeping Lorentz invariance by something that also carries mu. So the del mu, the fact that we have to compensate for something that partial derivative does, space-time derivative, forces us that these things will have transformation properties of a vector field. Why this strained transformation law? Because that's the way it fixes the non-invariance. Okay, so that's where the proof that I don't write. So doing that and giving A mu this transformation law, when you do the two things, it's a few lines, okay? So if you're very interested, do the exercise. Gives us that the transformation law of d mu phi is e to the iq theta d mu phi as we wanted. So we can achieve the goal of obtaining a Lagrangian that is invariant under a local symmetry with dynamical and scalar or fermion fields at the price of introducing a vector field with a specific transformation law. That's the way we can do it. And I said, why we want to do it? Because it seems that it applies in nature, as we will see. So the price, as I said, for obtaining invariance under a local symmetry is adding a vector field. And the vector field that is added is called a gauge field. And G, this dimensionless number that's allowed to appear there, is called coupling constant for reasons that will become soon clear. Now we added the field and we said, okay, so now we have our original fields, scalars, fermions, but we added the field and we said that every term that is allowed should be added. We added the field, so can we add more things? Turns out that we can add only one thing, which is a kinetic term for this A mu. And the form that is Poincare invariant is the following. You define something that is called field strength, F mu nu, which is d mu A nu minus d nu A mu. And this is the only allowed term. You cannot add any other term. So A appears in this derivative, okay? It's not the only place where it appears. It appears in this d mu, okay? It's inside it for the other fields. But other than that, the only thing that is not included in this d mu that you can add is this term. What does it mean? So this is now the most general normalizable Lagrangian that involves only a vector field and is invariant under a local symmetry. So first of all, if we were able to add kinetic terms, it makes this field dynamical also this vector field, we can now describe its propagation from one point in space-time to another. So, local symmetry forces us, if we want to impose it, to add a dynamical field of spin 1. Local symmetry and particles, spin 1 particles, are related. And let me tell you, and that's a more complicated mathematics, there is no consistent way to add a vector field into such a quantum field theory unless it is related to local symmetry transformation. The coefficient of quarter, oops, where did I go? Yeah. The coefficient of quarter is canonical normalization. If we choose this normalization, there is a straightforward interpretation of all the terms that involve this vector field. Very importantly, half of m squared a mu is not allowed by the local u1. It's interesting, at least for two reasons. One is a deep prediction. This vector field that you added must be massless. That's also part of the invariance under a local symmetry. It's a very strong prediction. So the only fields that we can add at this stage, vector fields, are massless fields. We cannot add a massive field. That will come later how we do it anyway. The other thing which is surprising, we said before that all terms that do not include derivatives and are allowed by global symmetry are also allowed by the local symmetry. That's true for the scalars and for the fermions. It's not true for the vector field. And the reason is that under the transformation, scalar and fermion fields go into a phase times, then it's a multiplicative transformation, e to the I q theta times the field. While the field, the vector field, goes under additive transformation. We add here, we add here this term. It's not a mu goes to a phase times a mu. It goes to a mu plus some, minus something. And that makes a difference. So if we had the global symmetry, okay, we could not incorporate a mu in a consistent way, but the mass square terms would be allowed by the global symmetry. But with the local symmetry, it's not allowed, and similarly, not quartic terms. Okay, there is here a comment that one, in addition to the f mu nu, one could include the terms which is epsilon mu nu rho sigma, the antisymmetric tensor with 4 indices, times f mu nu times f rho sigma, and it's a total derivative, which means that it's related to the value of this at infinity, if you want, which we assume to be 0. And for abelian symmetries, it has no physical meaning. It has no physical consequences. When we discuss non-abelian symmetries, that's not the case. This is just a side comment. We'll come back to it, perhaps. And there are no self-interaction. There is no a cubed, I know a to the fourth. So it doesn't interact with itself. So all these are consequences of the local symmetry. You want a local symmetry, you must introduce a vector field, spin related to spin 1 particle. It's massless, it doesn't have self-interactions. That's very strong predictions, okay? And the fact that in nature we know of the photon and the gluon that are spin 1, massless, and the photon does not have self-interactions at 3 level. The gluon does, but it's not an abelian symmetry, so we'll come to that when we discuss non-abelian symmetry. It's very intriguing, okay? We can explain it from a symmetry principle. The existence can be explained of the photon and the gluon can be explained by imposing a symmetry. I think this is impressive. Okay, so I mentioned already the fact that additive transformation and for a mu and multiplicative is the thing that for the a mu, not everything that is allowed by the global symmetry is also allowed by the local one. And finally, if you have several factors of local symmetries, local U1 times local, let's say U1b, for each of these separately, you need to introduce a corresponding boson that transforms under, let's say for this, a vector boson that transforms under the U1a and does not transform under the U1b. And for this, a gauge boson that transforms under U1b and does not transform under the U1a. And there would be two independent dimensionless couplings coming into the theory. We can call them GA and GB, or we'll see later how we call them in the standard model. Okay, so we've seen that imposing a local symmetry requires that you introduce vector field, namely spin 1, related to spin 1 particle that is massless and doesn't have self-interactions. And now we also deal with the first component here. It's not only, the charge is not only conserved quantity, but it sets the strength of interaction fermions with the photon. So let us see how that happens. So let's take a theory with a fermion, Dirac fermion psi, of charge Q. If it's charged, it cannot have Majorana mass terms, okay? So it must be a Dirac fermion, okay? In order to be a Majorana fermions, you need to have Majorana mass terms. If you have both Majorana and Dirac, the final situation will be a Majorana fermion, okay? So Majorana wins, but if it's charged, then no Majorana mass terms. Charge Q, that's, so a derivative acting on psi would be replaced, if we want local invariance under local symmetry, with this plus IGQ, A mu. Notice that Q appears here. I think it's probably written somewhere later, but let me say it now. While d mu is the same space-time derivative acting on any field, this d mu, which is called covariant derivative, is different for fields of different charges, okay? So since Q appears here, the exact form of d mu depends on which fields it operates. And it would have been nice if this was somehow mentioned in our terminology, if we would write here d mu, I don't know, subindex Q to suggest that, but the community decided, no, we'll write it this way. And so, but it's not the same. It depends on the field of which it acts through this Q. And so, in the kinetic term for fermions, for Dirac fermions, which we wrote before, psi bar gamma mu, okay, this was the kinetic term. Now we replace d mu, del mu, with this d mu, written here. So writing this, we get the original term as we wanted, because we want to be able to describe free propagation in space-time. And we have these additional terms related to this term here. Minus g q psi bar gamma mu a mu psi. And so here we have a vector field and two fermion fields. In pictures it's here. I'm sorry if it's not clear enough in the picture. So vector fields are appear in the Feynman diagrams in the pictures that we like to draw as a wavy line. Fermions is a solid line. So this is an interaction of a vector field with two fermions. So it could be, for example, such a vector field splitting into fermion-antifermion pairs, or a fermion emitting this vector field and continuing as the fermion field, and various other possibilities. And the strength of this interaction, as you can see here, is G times Q. Q, the charge that we assigned, and G is the coupling constant. So here is this comment that d mu depends on the field on which it acts. And second, what appears here is G times Q. And so we could decide, I don't know, to increase the now, if it only depends on GQ, we can raise G by a factor of 2 and put Q smaller by a factor of 2 and get the same result. So that's true, but as before, if we have two fields with different charges, then the ratio Q2 over Q1, or if you want GQ2 over GQ1, G is the same in all transformation. It's only Q that is changing. This ratio is physical and sets the relative strengths of interaction of psi2 and psi1 with the vector field A1. And the community decided on conventions of what to call this. We'll see soon when we get to QED. Okay, there is, the decision is that the electron carries charge -1, and with this convention, the coupling constants of QED, call it E instead of G, E squared over 4 pi is the famous alpha, 1 over 137. But it's in this convention. It's now such commonly accepted that we do not remember that it's a convention. We could increase all charges by a factor of 2, and then alpha would be smaller by a factor of 4 than what we know. Physics would be the same. Our decision, a convention. So, here is the comment that in the standard model, we impose only local symmetries. The only imposed symmetries are local. By the way, I think this is not written here. All accidental symmetries are global. You cannot get a local symmetry accidentally. Right? You need fields that are not there in the beginning. So that's impossible. Okay? So local symmetries are never accidental. They are only imposed. A priori, you could impose also global symmetries. You don't do it for several reasons. One is that there is understanding that gravitational effects, in particular black holes, violate all global symmetries. They can eat global charge and disappears there, and so the charge is not conserved if you want. And if gravitational effects break global symmetries, then it doesn't make sense to think that there are fundamental symmetries of nature if they are violated by some effects in nature. And the second reason is that, so this is a reason that it goes against the taste usually of the theoretical community to impose global symmetries. And the second reason, that there is no obvious motivation to impose such symmetries. The global symmetries that may apply in nature arise accidentally in the standard model. And so we do not have to. If they are violated in a problematic way by extensions of the standard model, then again, the good taste of theorists says impose a discrete symmetry that would give this global continuous one as accidental. But this, it's not a law of nature that there are no global symmetries, if you want. So, okay, we will not impose. We will go with the community. We will not impose we will not impose global symmetries. Okay, so now we made a further step in understanding the process of model building. You define two things, the symmetry and the charges of all fermions and scalars under the symmetry. That's the definition of the model. And then you write the most general and normalizable Lagrangian that depends on the scalar and fermion fields and is invariant under the symmetry. The added ingredient in that is that if the symmetry you imposed is local, then automatically you must add the corresponding gauge fields, the vector fields that compensate for the non-invariance of the kinetic terms. And in general, the Lagrangian can have 4 types of terms. The kinetic terms, for the scalars, the fermions, and if you imposed a local symmetries, then also for the vector field. Terms that are made purely of your fermion fields, and we said these are only mass terms, either Majorana or Dirac or both, depends on what is allowed. Terms that involve only the scalars, that the scalar potential, quadratic, trilinear, quartic, whatever is allowed, and Yukawa terms. Terms that are allowed and have a single fermion and two scalars. And so, after you define this, the kinetic terms are straightforward, they're always allowed, and we put them always, in this course, in the canonical normalization. And for each of these, you have to check what is allowed and what is not allowed, and write whatever is allowed. And once you did that, you go into the phenomenological implications, which I will mention again: the spectrum, the interactions, the accidental symmetries, the number of parameters, and then the experimental tests, or the number and the identity of the parameters that appear here. Okay, so we can go on to the next part. Let's see. I manage here. QED, I think. Control L. So, we go to a demonstration of something that is absolutely relevant in nature, QED. QED is the example of imposing a local abelian symmetry. So let us see how it works from this point of view, because usually it goes the other way around, and yeah, you kind of, when you start from elsewhere, the vector field A mu is not the main thing, while in this way of imposing a symmetry, this photon field is the basic thing that appears there. So I'm not sure how far we will get. In 20 minutes, we'll see. But this is an example of the things that I've been discussing in the last hour. So we'll start with one fermion. We'll define the model, QED. We'll write the most general Lagrangian, and then we'll do the spectrum, the interactions, the parameters. With one fermions, there are no accidental symmetries, so that's why it's not written here. I should have written here accidental symmetries, and I think it's written and say no accidental symmetries. And when we have two or even more, then there will be also accidental symmetries. So we'll see all of that. So here is the definition of a model, which happens to be QED. But the nice thing is that it's here more or less 2 or 3 lines, okay? And the full consequences of QED come out automatically. I impose a U1, I give it a name, okay? All U1s are the same, but this will relate to real things in nature, so I give it a name, U1 electromagnetism, and I introduce 2 fermion fields, E left and E right, that's the names I give them, with the same charge, -1, and no scalars. So now, the next stage, for each of these, I have to ask what is allowed and what is not allowed for the most general renormalizable Lagrangian. So, but first of all, I imposed a local symmetry, a local U1. So I'm required to introduce a single gauge field, A mu, and I give it a name, the photon field, okay? That's a name. And I define its field strengths, d mu A nu minus d nu A mu, and the covariant derivative, that's the thing that replaces the space-time derivative, is d mu plus I E, a dimensionless coupling, come back to it in a minute, Q, the charge of the field on which it acts, A mu. It's a little bit unfortunate that the community gave the electron, as we'll see, we later call the fermion, and the coupling constant, the same notation, E. But you will be able to tell from the context whether I mean the coupling constant or the fermion field to which I refer. Okay. L kinetic terms for all fields. We have 3 fields. kinetic term for the photon field, kinetic term for the left-handed E, kinetic term for the right-handed field, and here it's with the covariant derivative replacing the space-time derivative because I imposed a local symmetry. I gave both E left and E right the same charge. So there is one left-handed, one right-handed. I gave them both the same charge. It's a vectorial theory. And therefore I can write a Dirac mass term. I call the coefficient of that ME. It's E left bar, E right, plus Hermitian conjugate. And it has only a Dirac mass term because they are charged. So I cannot write Majorana mass terms for them. And there are no scalar fields. And so this part of the Lagrangian, which includes scalar fields, I have nothing to write there. And that's it. That's the Lagrangian of this model. Yes? It's coming, again, let me stress. It's coming from these two red lines. That's it. And that forces me to this Lagrangian. When I say I want to write a Lagrangian made out of these fermion fields and obeying this symmetry and only renormalizable terms. That's what I get. And this is the QED Lagrangian. So interpret it. What's the spectrum? I have a massless vector boson. There were no mass terms. Local invariants forbid them for the photon field, which is the photon. And I get a massive Dirac fermion. Its mass is ME. Since I wrote the kinetic term in the canonical normalization, then the coefficient of the quadratic term is the mass. And so, and I give it a name, the electron. Okay, name. And so say MA equals 0 is a consequence of the gauge symmetry. And a massless vector boson has 2 degrees of freedom. A massive vector boson has 3. It's not very important now. It will become important later. E left and E right are charged. No Majorana mass terms. They are vectorial. I'm allowed to write a Dirac mass term. So the electron is a Dirac fermion, which means it has 4 degrees of freedom. Interactions, including in this E d mu, E bar d mu E. So that's coming from the covariant derivative acting on the field E. And it's the photon field acting with electron, anti-electron, positron field. So that's the interaction. And in the convention that Q, that the charge under the U1 of this fermion field is -1, then E squared, here the coupling, over 4 pi is the famous alpha. 1 over 137 when I was very young, and I think now more people perhaps know it as 1 over 128 when it's measured on the Z pole. And so it runs from 1 over 137 to the very precisely measured of, not as precisely as the 1 over 137, but it's the famous one. And yeah, no photon self-interactions. The QED interaction is vector-like. It's with the same strength of the left-handed part of the electron and the right-handed, and it conserves parity, charge conjugation, and their product, CP. And so all these I did not impose, they are there. Has 2 parameters, ME and alpha, and they have been measured. I mean, you have to admire experimentalists for doing that with an accuracy of 10 to the minus 11. How can you measure almost anything? Well, I guess that the lengths of, in LIGO, of the 2 arms are measured with an accuracy of 10 to the minus 21, but okay. Anyway, I'm impressed, okay? So this is what we know about the electron mass. So this is the uncertainty on the last 2 digits, and this is 1 over alpha. So we know the values of these 2 parameters. Accidental symmetries, as promised, there are none. So this slide is empty. And let's see what changes if we add 1 more fermion. It's not entirely trivial, almost, but no, actually it's not trivial. So we go again through the process of model building. I impose a single U1, call it U1 electromagnetism, and now I have 4 fermion fields instead of 2 of the previous model that I built. 2 left-handed ones with charge -1, 2 right-handed ones with charge -1. No scalars. Okay, so the change from previously is now I have 2 of each of these. Okay, so what is allowed? Again, no L phi and no Lu kappa because there are no scalars. Kinetic, okay, for the photon field is the same as before, and now there are 4 terms. In the canonical normalization, they are diagonal, L1, L1, R1, R1, L2, L2, and R2, R2. And they have the same coefficient, this 1 -1 for each of them. We have, if you want, a 2x2 mass matrix. Because they carry the same charge, I can write Dirac mass terms that go like L left 1 bar, L right 1, L left bar 2, L right 2. And the Hermitian conjugate actually does the opposite combination. So this is the mass terms and no U curves. Now a trick. I change a basis, okay? I know it sounds like unfair, but I'll do it because I'm allowed to. So this is how the mass terms look in a matrix notation. Okay, there are these 4 entries here. And now I introduce V left and V right are 2 unitary matrices. So I put here a unit matrix. Okay? The unit matrix doesn't make a difference. It's the same Lagrangian. I put here unit matrix. I'm allowed to do that. But I choose V left and V right in such a way that this be unitary transformation. A unitary 2x2 matrix from the left, and in general another unitary 2x2 matrix from the right, so as to bring this to a diagonal and real form. I can always do that. It's always possible. And then it means, so now I put this V left and V right in parentheses, if you want, around the 2x2 mass matrix. It means that I move to a new basis. So this is the mass matrix for the right-handed fields, which are V right times L right 1, L right 2. This is not a symmetry, this is a change of basis, okay? There is no SU2, which would have been if this were. And so it is a change of basis. And so V left 1 acting on this, I call the fields in the new basis, the basis where the mass matrix is diagonal, I call them E left and mu left. And the right-handed fields, the one in the new basis, I call them E right, mu right. And in this language, in the new basis, these quadratic terms, the only thing that goes beyond the kinetic terms is ME E bar E plus MU. So that's ME and MU is the names I gave to the 2 entries here. And this is the new thing. So these 2 fields, E and mu, have well-defined masses, okay? So things have well-defined masses when the mass terms are diagonal, when they are in this form. The original fields here in general are not mass eigenstate. So I brought it to a basis, it's the same physics, but in the new basis, the fermions are mass eigenstates. With a single fermion, I didn't have to do it because there was 1 term and it was a mass eigenstate from the beginning. With 2 fields, I can always do that. And the mass basis is the one with the physical particles. Okay, these are the masses of the physical particles. We know whether electron or a muon hit our detector. And the electron and the muon are mass eigenstates. They have well-defined masses. So we have to come to this basis in order to understand what are the elementary particles and what is the spectrum. The fermion fields in this basis are called mass eigenstates. and we gave them names, the two mass eigenstates, the electron E and the muon mu. And what is the electron and what is a muon? Again, it's a convention, so we call the heavier field, the one with mu larger than mu, we call that one the muon, and the lighter one, the electron. In all other properties, except their masses, they are the same. They are spin half, they carry charge -1, and that's actually, and they are Dirac fermions. So all their properties are the same, except what distinguishes them are their masses, Me and Mu, and they are Dirac fermions. And in the language of the Dirac fermion mass eigenstates, the electron and the muon, this is how the Lagrangian looks like. Now, it's interesting because you can see here the terms with fermion has E bar E, mu bar mu, E bar E, and mu bar mu. You have no term which is like E bar mu. So we come back to that point in the next transparency, I guess. So the model with two, the U1 model, this QED with two fermions, has three parameters, Me and alpha of before, and Mu added, also known with not so bad accuracy, 10 to the -8. It's about 200 times heavier than the electron. So we imposed a U1 symmetry. And it's simple to see, that's why I mentioned it's only E bar E and mu bar mu in all terms, and no E bar mu or mu bar E, that actually we have a symmetry which is U1 under which only the electron transform, and a U1 mu under which only the muon field transforms. There are two independent U1s. You can do one phase transformation to the electron, another phase transformation to the muon. Since it's E bar E and mu bar mu everywhere, this phase transformation would cancel. And so, if you want, electron number and muon number are separately conserved. It goes beyond charge conservation. It tells you that these two species, the mass eigenstate, if the process starts with 2 electrons, it will end up with 2 electrons. If it started with 3 muons and 1 anti-muon, okay, the mu bar, it can end up with 2 muons, 3 minus 1, or as originally, but the number of muon, the muon number, which is the number of mu minus the number of mu bar, the number of negatively charged minus the number of positive charged, the antiparticles, that is conserved, this difference, separately for the electrons and the muons. So we have a U1 times U1. We imposed a U1, so this is, if you want, global, but part of it is a consequence, it's identical to the symmetry that we imposed. And so instead of writing it this way, we can write U1 electromagnetism, where under which their charges are equal, times a symmetry under their charges are opposite. There are various ways to write it. This is one of the ways. This is the imposed symmetry, and we got an extra accidental U1, and these are the charges under, okay, -1 and -1 are under the imposed symmetry. We assign them these charges, and plus -1 are under this new accidental symmetry, which came out of our renormalizable Lagrangian. And so, said electron number, number of electron minus number of positrons, and muon number, number of muons, number of anti-muons are conserved. So for example, mu minus going to E minus, E plus, E minus, which is allowed by the local symmetry, is forbidden by the accidental symmetry. Right? Because muon number initially is 1 and finally is 0, and electron number is initially 0 and finally 1. And again, accidental symmetry, if we included non-normalizable terms, it would not be there. We could, for example, write E left bar, E right, E left bar, mu right. It respects the imposed symmetry. It allows such a process. It breaks the accidental symmetry. It's not there because we only considered renormalizable terms. Okay. So even more fields. As long as we add pairs of left-hand and right-hand fields with the same charge, similar to the 2 Dirac fermion model, there is always a basis where the mass matrix is diagonal, and there is matching of pairs where such a pair can be combined in a Dirac field, and in the base basis, this is how the Lagrangian would look. Kinetic term for the photon field, we still have a single photon field. It compensates to all the non-invariances of the kinetic terms of the fermions, for each of them according to its charge. Okay, the covariant derivative depends on the charge, and there are the diagonal mass terms. The model has n plus 1 parameters, alpha, or if you want E, the coupling constant, and the masses of all the mass eigenstates, and there are n of these. And it has a U1 n symmetry. Each of these pieces, its number is conserved in all processes. One combination of these is the imposed U1 electromagnetic. All the other are accidental. This is the last transparency time. So QED is well known. I will not go into any details. Just there are numerous fantastic tests of QED. The photon should be massless. There is an upper bound experimentally of 10 to the minus 18 electron volt. I don't think you can prove it's massless because you need infinite accuracy, which you never get in experiments, but this is not bad. It doesn't have electromagnetic charge. The upper bound of this charge is 10 to the minus 35, that of the electron. And all of these, the magnetic, okay. Some of these perhaps have hints now, but I would not believe that they survive. Yeah, some of these terms you know from your undergraduate, I guess, numerous tests. And let me just remind you that it all started with essentially 2 lines here. And the rest was, including the existence of the photon field and electromagnetic interactions, was a prediction of these 2 lines, which is not bad an output for 2 lines. Okay, that's it. I think, yes.
Questions?
I spoke loud and slow, it seems. Well, I'm not sure, yes.
When you are looking at the local symmetry, so there we said that we need to add a vector field in so that all our things work out well. So is it that the scalar, we cannot have a fully scalar field in the local symmetry, like a local symmetry? If you want to impose into a scalar field, we need to add a vector a new term, vector field. That means we cannot have a purely scalar field if you are talking about the local symmetries.
Right. Mm-hmm. Yes.
So for every time we need to have that.
If you want a local symmetry,
okay.
Yes. A local symmetry requires a vector field.
Okay. And sir, in the last few slides where we were talking about the even more fermionic fields, can you just go there?
Yes.
So in the first part, as we are writing that as long as we add the left-handed, right-handed fields with the same charge, we end up with a 2 Dirac fermion model. So how with this are we going to get the tau1 particle also?
Yeah, so, yes.
How are we going to get tau1 particle from it if we are...
Tau particle.
Yes, sir.
Yes, so this is with 3 pairs. If I had L1 left and right, L2 left and right, L3 left and right, all of them with charge -1 under U1 electromagnetism, I would get 3 mass eigenstates. I would now call them, so I would go to that basis. In general, I start with a 3x3 matrix. I do a unitary transformation, a B unitary by 3x3 unitary matrices. I get to the diagonal basis. I call the fields in that basis E, mu, and tau. And by definition, m tau larger than mu larger than me, where these are the three entries in the diagonal mass matrix. And now I get these three fermions. And actually, you can extend it even beyond the case where all the fermions carry the same charge. So in the standard model, as far as the QED part of it, QED is part of the standard model, okay? As far as it is concerned, you have the three fields with charge -1, E, mu, and tau. You have the three fields with charge +2/3, top, charm, and up, and three fields with charge -1/3. And the QED, the Lagrangian, looks exactly like this, except that, or not except, exactly this. These d mu, there are now, in the standard model, there are 9 charged fields under U1. So in 3 of them, d mu, which has in it Q, the Q will be -1 for the E, mu, and tau. For the 3 up quarks, it will be +2/3. And for the 3 down quarks, it will be -1/3. But it will have exactly this form for all charged fermions. All the charged fermions are Dirac fermions in the standard model. Yeah.
Thanks.
So this question is related to local symmetry and global symmetry. So when you said that local symmetries are imposed and the global symmetries are accidental one.
The first part I fully agree. Local symmetries are always, you cannot get a local symmetry as an imposed symmetry. You can impose a global symmetry on your model. It is commonly believed, but I don't think there is a rigorous proof, that global symmetries are not fundamental symmetries of nature because they are broken by gravitational effects. And so there is a preference not to impose global symmetries, to get them accidental symmetries. And in cases where your model cries for imposing, let's say the supersymmetric standard model, which violates baryon and lepton number, then you impose a discrete symmetry, which is okay, can come from, and that discrete symmetry leads to the global continuous symmetry is accidental. But that's not a rigorous statement. You can, if you want to impose also
I can do that.
Global symmetries.
But the problem with the gravitational effect.
Yes, so probably. I don't know if there is a general proof or black hole. I'm not sure what the consensus is now.
Global symmetry are essentially the part of the local symmetries?
No, they go beyond. So, for example, that the QED interactions conserve electron and muon numbers separately. It's not part of the part of it. It is the sum electrons plus muons minus positron minus anti-muons. That's the imposed symmetry. But the other part, electrons minus muons plus anti-muons, that's not part of the imposed local symmetry. That's accidental, and if you allow non-normalizable terms, they will break it while respecting the imposed U1 electromagnetism.
Okay. Thank you, sir.
Sir, for two fermion model, you start with a 2x2 mass matrix.
Yes.
That means you have 8 free parameter if we consider a complex mass matrix.
Yes.
But after diagonalizing all these things, we have only 2 free parameter.
Right.
So how this 6 parameter is actually omitted?
Yeah. So the number of physical parameters, one should be careful not to guess it from the way you write the most general renormalizable Lagrangian. It's not the correct counting. You should count it in the mass basis for all fields. And it's more often than not that the number of physical parameters is smaller than the number of parameters that appear in the most general writing of the Lagrangian. So what does it mean? It's not that you are not allowed to use the Lagrangian in the most general way it's written, okay? You can use the Lagrangian in this way. Anytime you calculate a physical observable, it will not depend on all of these parameters independently of each other, M11, M22, M12, and M21. It will only depend, this is a combination of these, so it will only depend on these two combinations of what seems to be 4 parameters. So that you will realize that when you will calculate a physical observable. The physical observable depends only on this, and a shortcut to this is to write them in the mass basis. Even then, there are still things that you can do to remove further parameters. For example, there is something famous called the CKM matrix, which characterizes the couplings of the W boson to quark-antiquark pairs. It's a unitary 3x3 matrix. In most general form, it has 3 real parameters and 6 phases. But there is an additional freedom by which you can remove some of the phases and remain with just one physical phase. So again, you could use the most general form of this unitary 3x3. You will find that only one combination of these phases appears when you calculate a physical observable, and that's the single phase that is known as the Kobayashi-Maskawa phase. It's a combination of, and any other combination of the phases never appears in a physical observable.
No. Anyone else? No? Can you
Okay, so let's start from there. We now go back to the block for the T and forward interactions.